Welcome back to the course on architectural design of ICs. So, in the last class we have seen that how we can optimize based on the restricted fan in or fan out option. Okay. So, how we can that means optimize the CLA whenever CLA in terms of that means whenever we are generating the carry or we are writing the expression or implementing the expression for carry. So, at that time how we can define the fan in for each of the levels, whether I can, that means if I restrict the fan in. So, at that time obviously it will increase the level. So, what will be the group size and then what will be the level size. Based on that we have seen 4 kind of topology, and based on that we have seen that the variable size implementation of the carry logic is it is better than the, in terms of delay consumption, it is better than the fixed implementation of the same carry expression. Okay. So, again today we will start with another architecture of this adder, which is carry select adder. Okay. So, we will start this carry select adder by this name of it, this carry select adder. It says that we have to, based on this selection of the carry, can I do this addition operation? That means what is the intention? To make it faster. Okay. So, how can we do this carry or what is that means working principle of this carry select adder? So, in the carry select adder, in the ripple carry adder, what we do? Basically, we in each of this case we consider this full adder cell, then this carry is basically propagated and at the output we get the final carry out, and each of this particular case we got the sum bit. But in this carry select adder, what we do, instead of that we do parallelly to that means ripple carry addition operation. For what? One, considering this carry input as 0 and another one considering this carry input bit to 1. Okay. That means why I need to do that? Because in case of this this ripple carry adder, that means if my carry input bit, if that is 1, suppose I need to add 1 1 0 0 along with this 0 0 1 0. Okay. So, if I just want to add, if my carry input bit that is 0, so at that time it will just this, but if my carry input bit that is equals to 1, so at that time it will be something like this, that means the value will be changed. Okay. So, in this particular case what we are doing, at the very last level, we are, that means we have, suppose 16 bit, this is the 16 bit carry, that means select adder architecture. So, 16 bit carry select adder I have to design. So, at that time how can I design or how I can start with the design? That means, now what we are doing, we are making the 4 bit group. Okay. So, each of this is 4 bit. And this is also 4 bit. So, at the very last of this, that means at the very last group, what we are doing? We are not following the corresponding carry select addition. What is that means main idea behind carry selection adder operation, that means operation. So, that we are not doing. So, what we are doing from here, actually again if I just want to that means go back to this. So, if I just this if I just divide, so at that time means what? I am having this particular 4 block. So, this carry is basically coming over here. So, this is but nothing but this ripple carry adder. Okay. Now, based on this, what I said, if I just want to add this particular value, suppose 1 0. So, in one case if my carry input bit is 0 and if my carry input bit is 1. So, whenever this is 0, at that time what value I am getting? I am getting 14, for this I am getting 15. Okay. So, that means here from the beginning I am calculating this 14 and 15 from the beginning. Now, based on this carry input bit, carry output bit of this particular LSB side, now I will choose what value I will select. So, that means if this bit is 1, so at that time I will select this 1 1 1 1 over here. If this bit is 0, so at that time I will go with 1 1 1 0 for this particular case. Now, as this is also not producing any carry over here. So, again this value again it will have 2 of these sum bits. So, 0 means I will choose this particular case, I will not choose this case. Again for this is also there are having 4 of these sum bits and its carry output bits. So, based on this carry output over here, so it will select the corresponding things. So, that means what is the main that means fundamentals here? The idea behind this is that whenever this is over, that means now I am doing what? I am parallelly basically computing all the values of this, sum bit of all this I am computing parallelly. Okay. Considering, because carry in that should be 0 or 1. So, both the case I am computing at once, that means all the input bits are available to me, right. So, in ripple carry adder where is the problem? Unless and until I am getting this carry input over here, I cannot start this operation. Again, unless and until I am getting this carry over here, I cannot start it operation. But here what we are doing from the beginning, or by putting 2, as we know that carry input as it is a binary, that means signal. So, it will have either 0 or 1. So, considering that fact, from the beginning parallelly all these blocks are running. That means for 0 computation it is doing, for 1 considering 1 carry input bit to 1 also it is doing. Now, the thing is that whenever I will get this carry input bit, there is a marks, based on the marks. So, I will get 2 of this sum. If I just go back to this. So, that means I will get for this A7 B7 I will get 2 sets of this particular sum over here. Okay. So, the sum, this is basically the sum for this considering carry equals to 0, and this is the sum for considering the 1, and again for this is for 0, this is for 1. So, now if this bit is this carry output bit, if it is 1, then it will choose all the sum bits from 1 only. Okay. And again whatever is the carry output from this particular block, this is for 1, this is for 0. So, for this carry output again it will come over here for the next 4 bit group. So, again this will choose based on the same logic. So, that means here then what is the problem here? The problem is that we are exploiting, that means we are increasing the, or that means we are increasing the speed, or we are basically decreasing the critical path in corresponds to carry loop this ripple carry adder by exploiting more number of hardware or more number of adder. That means here what I have done, I have just replicated the 4 bit full adder twice. So, that means initially for ripple carry adder I was needing only one set of this, but here I am needing 2, and then again I need at the output I need some extra multiplexer. But here the delay, if I roughly estimate, I can reduce the okay. So, that means initially what we are taking, not actually this is roughly estimation, I am not telling this is the final one, because as there is the marks. So, again it will take some of its time. Okay. So, I can reduce the corresponding delay. Okay. So, the maximum delay will be what? It will comes from this particular case to. So, the carry is basically now traversing to this particular paths, right. So, this is the, that means corresponding delay for this particular path. So, here you see this is not that, and this is connected to only that means one of this particular multiplexer, that means as this is running in parallel. So, this bit is basically connected. So, here I will get this 4 full adder delay, and here 1, then 2, then 3, then 4, then 5, then 6, then 6 plus 6 multiplexer delay. Okay. So, that I will get for this particular circuit. Okay. So, if I just go to the next slide. So, the same thing here you see in the that means in the this in the previous slide, what we see that we are considering 4 of this. Again what we can do, we can just do it in a different way, that means we can select. In case of carry skip adder, what we have seen that in the middle portion, if we chose the size of that means the more the size, we can get or we can reduce the delay critical path in a better way than if we use fixed number of that means groups for each of these, that means fixed number of bits for each of these groups. Okay. So, in this here also we are doing this grouping, right. In this particular case, can you do something, do that kind of things to get the reduction in critical path? Okay. So, here also we can do. So, here what we are doing, actually in the last if I just go back to the previous. So, what I said that for this I need 4 full adder delays, and then I need this total 6 multiplexer delay. Okay. Then if I just reduce this only 2 full adder cell, that means the last level, then that 4 full adder cell delay, that will be reduced by 2. Okay. So, then that 2 is now passes through, then 2, then 2, then again that is 3, then there is 4, then there is 5. So, that means now the group is like something like this 2, 2, 3, 4, 5. That means now the delay will be something like this, what? Here 2 full adder delay, then 1, 2, 3, 4, 5, 6, 7, 8. So, 8 number of multiplexer delay we need to use. So, now another thing also we can do, what we can do. So, here we are using this, that means the last 4 bits that we have just initially we have just distributed it in 2 way, that means 2, 2. Then this another 4 group that we have divided something like this 5, 4, 3. So, 12 bit was there, that has been divided in 5 4 3, or else you can try with that 4 4 4 here 2 2, that also possible. That means now it depends, that means it is basically how this 16 bit operation, how we can distribute this. You can distribute via like 4 plus 4 plus 4 plus 2 plus 2, or you can distribute 5 plus 4 plus 3 plus 2 plus 2, or you can 4 plus 4 plus 4. So, that means this 16 bit, that you can group in combination of different groups, okay, of different, that means each group of different number of bits, that you can consider. So, whenever you will consider this, so considering this means you will get for different of this, that means topology, you will get different delay, and among them which one will be the, that means we from for what combination you will get lesser delay, that will be your ultimate combination for implementing the carry select adder. But here what I said, that I am increasing, initially if I used this 16 full adder cell, here I need to use how many, that means let us consider for this particular case, if I just exclude 2, then for 28, so 30 full adder cell for this particular combination. Okay. So, for 444, so how much? So, in it, that means 12, 28 number of full adder cell. So, if I consider this, so at that time 5 4 3 2 2. So, then that means 2 3 5 10. So, here for here also, that is 30 full adder cell. Okay. So, that means now I have increased the full adder cell to 30 or 28 or something. Along with this, I need more of the multiplexer over here. So, if I am considering 2, that means 12 plus 1 2 3. So, total 15 number of multiplexer again I need. Okay. So, that means I am increasing, or I am, as I said, that whenever I need to gain something, at the time I have to lose somewhere. That means exploiting extra hardware to the circuit, I can reduce the delay in a very much in a certain way, or that means the delay reduction here, that is in a good number. Okay. So, based on or this following this particular that means this logic or this idea, again the people have developed another architecture, which is the, that means the fastest adder, okay, and possibly the fastest adder, which is the conditional sum adder. So, that we will see, that architecture we will see now. So, here you see carry select adder, that combination of 2 32 bit variable, this adder in select mode, okay. That also we can do, but so what I said, that based on this carry select that means adder logic operation, okay, we develop this conditional sum adder, and this is the possibly the fastest adder. And if you just want to that means know more on this conditional sum adder, you just follow this particular that means papers, which is in published in IRE Transaction on Electronic Computers in 1960. So, here what actually we see that for this input of x and y, considering this carry input of 0 and carry input of 1, I can get two different set of carry that means bit and sum bit, for this is for carry input 0 and this is for carry input to 1. So, that means for this I am getting this this CM0, CM1, S1 and S0. In the that means where is the difference here? So, in this particular case I am not considering bit wise. That means here I am considering 2 bit at a group, that means this is a full adder, 2 bit full adder, that means 2 bit ripple carry adder, this is a 3 bit ripple carry adder, this is 4 bit ripple carry adder, this is 5 bit ripple carry adder. But I have not considered individually to this particular full adder cell. Okay. So, in conditional sum, so for each of these bits I can get two that means different set of sum and carry value considering the carry input to 1 or 0. So, that is why this is a conditional adder considering this x and y are the two inputs, and I can get for this is for 1 sum this carry 1 and sum 1, this is for considering this carry output is 0, that is sum C 0 and S 0. Now, if I just want to that means design one 8 bit conditional sum adder, then how can I draw that or how can I design that 8 bit conditional sum adder? So, this is the final architecture of 8 bit conditional sum adder. So, if I just explain or if I just want to that means how this is basically works, what is the working principle of this particular 8 bit and conditional sum adder, that you see at the very of this at the very beginning of this, okay, this is x 0 and y 0, and from here considering the C in I can get the sum 0, right. Now, this will produce the corresponding C 1 over here, right. Now, in the next what happens, I am having this 2 number of full adders, this conditional adder considering one for 0, another for 1. Why I have not considered for this particular LSB position? Because this C in is the external signal, okay, which is directly coming to this particular point. So, that is why I do not need this particular multiplexer operation over here. But I do not know here what we are basically following, we are initially guessing that okay, that might or we are predicting the sum and carry value considering the carry input bit to 0 ones and 1 ones. So, we are just getting the or obtaining the results of carry and sum in this particular from these two particular full adder cell. So, whenever this full adder, that means the carry out from this full adder cell is 1, this is 1 means it will choose the full adder output, the carry and sum output from this particular full adder cell. Okay. That means, whenever we are computing this the corresponding sum and carry, at that time I am also computing the sum and carry for this y1 and x1 too. Only generation of this is now taking the decision which signal, whether I need to pass the full adder cell from this particular that means path or I need to pass the signal from this particular full adder cell, whether that is for 1 or for 0. We are taking the decision through these multiplexers. So, from here now I am getting the S1. So, in the next what from this again I will get the So, in the next I will get this sum, that means the carry from this particular blocks too. So, whenever we will consider the second case, in the second case I have to consider this this for y2 and x2. That means, here we have considered x0 y0, then we have considered y1 x1. Then here for y2 and x2, again we are considering this 0 for this 0 and 1. For y3 x3 also 0 and 1 we are considering, right. Okay, we will actually, it needs more time to complete this particular that means circuit for explanation. Okay. So, for today we will just stopping the lecture at this point. So, in the next class we will start from this particular point on this conditional sum adder. We will see initially we will see this how this architecture basically works, and then we will take one example and how the data is basically finally compute the final results, that also we will see in the next class. Thank you.